Tonight, though, is really the beginning part of tonight is really about how to determine or predict the concentration of a reactant at a specific point in time. So, how can we get the concentration of a reactant at an instant in time? So, how can we get it? What will the concentration of this thing be after the reaction has gone for 185 seconds, right? That's what tonight is all about. And in order to do that, what you need is some calculus. Luckily, that calculus has been done for us. So by taking your traditional rate laws and integrating them, okay, mathematicians have come up with these integrated rate laws. Okay. Now, if a reaction is zero order, first order, second order, they are all going to have different integrated rate laws. So the equation that we use to predict the concentration of something at a specific point in time, that's going to be different whether or not we're looking at something that's zero order, first order, or second order. So we're going to get three equations here. You do not need to know how to derive these equations. Remember, you are getting a formula sheet for the first test, right? So this is really all about, can you use these equations to do various things? So here is our first one. Our first integrated rate law, and you should write this down and put stars around it. Our first integrated rate law is our zero order integrated rate law. And it is the concentration of a reactant at time t, that's what the subscript t means, is equal to the negative rate constant times the temperature, probably in seconds, right? Plus the initial or starting concentration of that reactant. Here's the most beautiful thing about this equation. It is in slope-intercept form, right? So I'm going to take you back to Algebra 1, right? A little scary, okay? For me, that was Mrs. Snavely, so super scary, right? Nothing against Mrs. Snavely. She's probably dead. Anyway, so you can notice that this is in integrated, or I'm sorry, this is in slope-intercept form, where y is the concentration of A times t. The slope is negative k. Time is the x, okay? And the y-intercept would be that initial concentration of A. So if we look at a graph for a zero-order reaction, again, y-intercept is the initial concentration. We got the concentration on the y, time on the x, and you'll notice we give a negative slope, negative k. So if we could get the slope of this line multiplied by -1, that's going to be the rate constant k. Okay, so this is our first integrated rate law. You'll see how we use these in a moment. So that's for a zero order equation. What if something is first order? Well, if something is first order, and I would say first order is probably the most common order for a reactant. If something is first order, here's the equation that we use. The natural log of the concentration times t is equal to negative kt plus the natural log of the initial concentration. Okay, so once again, slope-intercept form, y equals mx plus b. Zero order and first order have something in common. They're both negative slopes, right? So the slope for both a zero and a first order equation is going to be the negative rate constant. Yeah, people tend to struggle with this one a little bit, maybe because of the natural logs. So, if I'm solving for the concentration at time t, then we have to undo the natural log. We'll review how to do that, right? Usually it's just second natural log, right? So e to the 2.71 repeating or whatever irrational number to that as a power will undo the natural log. Sometimes people rearrange the integrated rate law for first order equation. I don't think that's very useful. I think it's best to keep it in slope intercept form. So this is the next equation that you want to write down, put stars around, and make sure it gets onto your formula sheet. The last integrated rate law, and again, we're going to use these in a moment. We're just getting them right now. The last integrated rate law is for a second order reactant. And this one looks different. If we look at the graph, obviously, this one has a positive slope. If something is second order, you can predict the concentration at specific points in time, or you can use this to figure out how long it'll take to get to some concentration. This equation obviously looks different, okay? Because we have a different kind of a graph, right? So it's 1 over the concentration of A times T is equal to positive K. So here we have a positive slope times the temperature plus 1 over the initial concentration. So our y-intercept is really the inverse of the initial concentration, 1 divided by that. And again, 1 over the concentrations are on the y, time is on the x, and we got a positive slope for k. Yeah, what's up, Brandon? Did you try to raise your hand, Brandon?
Does the
What's that?
yeah, yeah the subscript 0, does that just indicate the initial rate?
Yep, means starting. That subscript 0 is the starting concentration. So what did you start with? Did you put 0.5 molar solution in there? Whatever, right? So in each one of these integrated rate laws, when you see that little 0, in science we call that the null symbol, right? Okay, so like in physics, like V0 would be the initial velocity or whatever. Um, Come on, mouse. But this is just starting concentration. So what did we start with? So the amount of time it takes to get to a specific concentration depends on how much you started with for each one of these, right? Okay, because if I started with a whole lot, okay, then it's going to take longer to get down to something than if I didn't start with as much. So that's why the initial concentration matters. Yep, cool. Graphing, super powerful tool here. Obviously on the test, and I wish I could, if I wish I could give each one of you like a laptop and give you Google Docs or Excel and have you solve for whether or not something is 0, first or second order using graphing, because it's pretty awesome. But I'm not. I used to do a homework where I made you do that for homework. I made you go to Google Sheets and graph it and stuff. But I do want to show you how this works, because in the real world, in the lab, a lot of times what we do, we'll run a reaction, measure the concentration at different points in time, and then we make a graph and see which graph gives us the best fit for our data. And then we can determine if something is 0, first or second order. So for example, say that you had some way to monitor the amount of this reactant, or I should say the concentration of this reactant as the reaction progresses. So say at T equals 0, you start with a 0.1 molar solution of, or 0.1 molar concentration of this gas. And then you're able to monitor how much is in there in 100-second intervals. So after 100 seconds, it's down to 0.0971. After 200, it's down to this. And you do this for 1,500 seconds, right? What you could do is put that data in Excel and make Excel do the work for you. It's pretty awesome. And I do just want to show this. So I have exactly that. If you give me a second, I can show you how this would work in the real world, okay, as opposed to like in a textbook. And I think that's important, right, that you get a mix of both. So here's that exact same data. I just typed it all into Excel here. And I want to show you how this would work. Okay, so I can show you how fast this is once you have all your data entered. The first thing we can do is check the 0 order fit. So 0 order is concentration versus time. Okay, and all we would have to do is make a graph. So you would do an XY scatter plot. And we're just going to name this 0 order. And then to determine how good of a fit it is, we would add a trend line. We would make it linear, and we would put the equation and the R squared value on here. So this tells us, so I don't know if you've taken statistics or not. If you haven't, that's fine. But R squared is this like correlation factor, and it tells you essentially how good of a fit this straight line was to that data. The closer it is to 1, the better. R squared of 1 is a perfect fit. That means you can draw a straight line right through the middle at each one of those points, and it's a perfect fit for that data. So if you look at the 0 order graph, that's a pretty good fit, okay? But we're going to check first and second order. Maybe one of those is a better fit. And if this turns out to be the correct graph or the best graph, then right there is your rate constant, 2 times 10 to the negative fifth. Remember, the slope for a 0 order equation is y equals, well, here, I'll write it. I can type it out. If something was 0 order, remember, it's the concentration of A at time t, okay, equals negative K T plus the initial concentration of A. So right there, concentration at time t is equal to negative K. So K would be 2 times 10 to the negative fifth. And then that must have been the initial concentration. So let's try a first order fit, and I want to show you just how awesome and how fast this is if you're doing it in Excel. So there's my zero order graph. I'm going to move that off to the side. We're going to make Excel do all the work for us. So now we need the natural log of the concentrations for first order, right? Integrated rate law for first order reactions, the natural log of the concentration of A at time t equals negative KT plus the natural log of the initial concentration. So we can make Excel do all that math in like 25 seconds, right? So we just do equals natural log, parentheses of that cell, close the parentheses. Then we use that crazy awesome fill down tool. Boom, there's all the natural logs. That took what? Less than 10 seconds, right? Now we can select time and the natural log data, and we could do the exact same thing. We can insert this graph, and that's looking pretty darn straight. So here is our first order graph, first order graph. And now we're going to do the same thing. We're going to add a trend line. We're going to put the equation in the R squared, and boy, I don't think it's going to get any better than that. Here we have an R squared value that's perfect. It's perfect R squared value 1. That never happens in the real world, by the way. That only happens in the fantasy world of textbook problems. Okay, but we got an R squared value 1. That means it's an absolute perfect fit to our data. And then this would be our slope. Our slope would be negative 0.0003. That's only got one sig fig. Ideally, we probably want to change that and get more sig figs. And you can make Excel do that for you. But our rate constant would be positive 0.0003, okay, or whatever that is with more sig figs. Just for completeness sake, just in case there's a better fit for second order, let's check the second order. For second order, we need to do 1 divided by all these concentrations, right? So we can make Excel do that. Equals 1 divided by these concentrations. Hit enter, fill down, and then select, insert, XY scatter graph. And now you can kind of visually see this is not going to be as good of a fit. We're going to add all this stuff. And there we go. It's only an R squared of 0.9965. So obviously looking at the best fit was that first order. And the the zero and the second order were all okay, but the first order was easily the best. So yeah. And then once you play around, you can really, you can go back, you can label the axes, you can make this give you more sig figs for the slope, but that would be the best. So what I hope you get out of that is that, if you ever go ahead and get a job in a lab where you're studying kinetics or something, that's a skill that you're going to develop, right? Enter all that kinetics data into Excel and then play around with it, right? What's the best fit? Just straight up concentration versus time, then it's zero order. Natural log the concentration versus time, then it's first order. 1 over the concentration versus time, then it's second order. That would be how you would do it in the real world, okay? Now, obviously, though, like on a test and stuff, I can't, make you graph it. But I just wanted you, and then here I did make Excel give me more sig figs, so it's 2.90 instead of just 3, right? Times 10 to the negative 4th. All right. I want to actually use this data. So we went through all that work. We figured out that this reaction is first order. So we now know the reaction's first order. So the first order integrated rate law is what we would use to solve for any equation that deals with time, because we just proved that this reactant is undergoing first order kinetics, right? So we need to use the first order integrated rate law. And we actually have the K value, 2.90 times 10 to the negative 4th. And I'm going to write that down on the board because my short-term memory certainly is not not what it used to be. So here's our equation, and we have the rate constant now for this. And I want to say if the previous reaction was run at the same temperature, what would the constant, and that's important, same temperature means we can use that rate constant we just got. What would be the concentration of SO2Cl2 after 865 seconds? So I'm going to steal that off of there. We know the time is 865 seconds. And the initial concentration, so the starting concentration of SO2Cl2 is 0.0225 molar. And I want to know the concentration of SO2Cl2 after 865 seconds. That's what I'm looking for. So that word problem right there boils down to this. Okay, if the rate constant for this reaction is 2.90 times 10 to the negative fourth, okay, and seconds to the negative first. Why? Because it's first order, and that's the units of the rate constant for a first order reaction, right? So if this is my rate constant, I want to know if I start with this much reactant, after 865 seconds, how much is going to be left? That's the problem. So we need to whip out our integrated rate law for first order reactions. So here we go. The natural log of the concentration of the reactant at time t, which is 865 seconds, I'm just going to put that down there, is equal to negative k times t plus the natural log of the initial concentration of the reactant. So that's the equation. Now we're going to plug and talk about chugging it, all right? So here we go. We're solving for this. So if you want to call that x, you're welcome to. Okay, so the natural log of x, right? Or you can keep writing that. Doesn't matter. That equals negative rate constant, negative 2.90 times 10 to the negative fourth seconds to the negative first. Or you can write that over seconds. Doesn't matter to me. Times the time, which is 865 seconds, plus, and I'm running out of room here, the natural log of the initial concentration, which is 0.0225. So the only unit I see canceling out is the seconds, right? So what are we going to do? Well, we can plug this in our calculator, or you can break it up into two steps. So we could multiply those two if you want. Negative 2.9 e negative 4 times 865. That's negative 0.25085 plus, we can get the natural log of 0.0225. That's a negative 3.794. Now we can add those together. We end up with the natural log of the concentration at time t is equal to negative 4.045. But I don't want the natural log of the concentration at time t. I want the actual concentration. So how do we undo natural log? If you look on your calculator, if you find that natural log button, it's usually like second that button. So if you look on a TI-83 or 84, it's that e to the x button. Whoops. Natural log is an irrational number like pi. Pi is 3.141. E is natural log is just based on an irrational number like pi. This irrational number is e, which is 2.71 something something something. If you take calculus, you'll use a circle to solve for e. I remember doing it once in my life, right? And I couldn't do it again, but I remember doing it once, and I was like, oh, that's where e comes from, or that's one of the places where e comes from. Anyway, we need to do that e to the function on both sides. So if you just hit second natural log, not log, that's base 10, you want natural log, and then you take the e to that, you'll find that the concentration after 865 seconds has gone down to 0.0175 molar. So this may not seem powerful, but it kind of is. You're able to like predict the future, right? Which is heavy, man, right? You started with this concentration, and if we know the rate constant for the reaction, then we could predict how much will be left after any amount of time we want. We picked 865 seconds, and after 865 seconds, this concentration will have gone from 0.0225 down to 0.0175, right? So it's pretty powerful, this equation. So that's what now if the reaction was zero order or second order, you would do the same thing that we just did, but you would just use the zero order or second order integrated rate law. This one was first order, so we do that. Now I do say first order is probably the most common, and I would say people tend to struggle with it kind of the most because it's got the whole natural log thing in there. right? So people forget how to undo natural log and all that stuff, but it's not that bad, right? Let your calculator help you. It's the second natural log that allows you to undo that. Whoops. All right, did we get the same thing? Yeah, we got the same thing that I got 8, 9 years ago when I made this slide. That's good. That's always good. All right, let's take a look at this bad boy. It is determined that the decomposition of nitrogen dioxide occurs via a second order reaction. Now, I technically wouldn't have even had to tell you that. Why wouldn't have I had to tell you that? Because if I'm giving you this graph, folks, you should be able to get that, man. Look at the graph. It's 1 over the concentration versus time. And the other thing is it's got a positive slope. If you got a positive slope to one of these integrated rate law graphs, it's got to be second order, right? The 0 in first order had that negative slope. So we got a positive slope here. The graph below yielded a straight line. Beautiful. What will the concentration of nitrogen dioxide be after 30 minutes? If y'all give me a second, I'm going to erase this board and copy down the important information that we need. Okay, so we have an equation of the line, best fit. We know it's second order. We want to know how much will be left after 30 minutes. Okay, so the first thing I would do is, since this is second order, is I would write the integrated rate law for a second order reaction down. So let's write that down. The integrated rate law for a second order reaction is 1 over the concentration, in this case that's NO2, initial, is equal to positive KT, oh no, not initial, oh my goodness, at times T, which is going to be 30 minutes here. We got a problem with that. We're going to have to fix here in a second. Equals positive KT plus 1 over the initial concentration. Okay, here's our problem. This graph was in seconds. The time was in seconds if we go back and look. So this rate constant is going to have units of molar to the negative first times seconds to the negative first because it's second order. So the problem is I cannot plug a time in minutes when my rate constant is in per second. Okay, so I would convert that time. That's an easy conversion, right? 1 minute, 60 seconds. So that's 1,800 seconds, right? Okay, I better check it. It's late at night, right? 30 times 60, 1,800. So that's what's going to go in for time. And we have everything else, right? We have the slope, 0.255. We converted our time to seconds, and we have 1 over NO2 is 100. Okay, so the 1 over the concentration of what we want is equal to 0.255 times 1,800. Okay, and if you want to put the units on there, it is molars times seconds in the denominator because it's second order, plus 100. That 100 is already the 1 over the initial concentration. So now this is really easy, right? You can just plug that right on in your calculator. 1 over the initial concentration after 30 minutes is equal to 0.255 times 1,800 plus 100. And you're going to get 559. But here's the problem. I don't want 1 over the concentration. I want the concentration. So what do we need to do? Well, you could do 2 things here. You could do 1 divided by that, or taking the inverse of something is the same as raising it to the negative first power. So there's even a button on your calculator, that X, most calculators, that X minus 1 button, that's the same as finding the inverse or taking 1 over that. So however, if you want to do 1 divided by 559, or you want to do 559 to the negative first power, whatever, we get the concentration of NO2 after 30 minutes is equal to 0.00179 molar. So if this is the reaction we were running, and we can figure out what we started with here. If we do the inverse of 100, right? So inverse one is going to be 0.01. We started with 0.01 molar, okay? Because I know 1 over the initial concentration was 100, so the inverse of 100 is 0.01. We started with 0.01. molar of NO2. After 30 minutes or 1800 seconds, we've gone from 0.01 down to 0.00179. So, yeah, that would do that. A lot of times, once you figure out if it's zero first or second order, the first thing you're going to want to do is write down the integrated rate law. So as soon as we knew this was second order, I'm going to write down the integrated rate law for second order. I'm going to say, okay, I have this stuff, and it's just a little bit of algebra, just a little bit out. So there was a second order problem for you.